get started. We have Ryan and Dustin here from Fluence, and they're going to walk you through their webinar. One thing to note is we will take questions in the chat throughout the presentation. They'll try to answer them as they come in, so it'll be a little bit more of an open dialogue. So feel free to throw those in the chat, and they will be watching for them, and we'll try to get to your questions. So with that, Dustin, Ryan, we'll let you take it away. Thanks so much.
Thank you.
Thanks, Jessica. Hey, everyone. My name is Ryan Petronella. Real quick, just to start off, break the ice, I wanted to share a few personal pictures. Really passionate rock climber. If you can go back, Dustin, the photo on the left that you see there is Zion National Park. For those events in southern Utah, beautiful place. I really enjoy a style of climbing called big wall climbing, which is typically, multiple days on a wall. That picture on the left, I'm hanging out on a portaledge about 1,000 feet up on a feature called Moonlight Buttress. The right there is one of the most famous climbs in the world called the Nose. That's up the center of El Capitan in Yosemite. And that move there is called a pendulum. It's the king swing off the boot flake. You can see that big rock that kind of looks like a boot. So I'm hanging out on the right there, and my partner Mar is swinging back and forth to gain momentum to swing over to the crack system on the left. Next picture is from down south. That's Patagonia, looking at Cerro Torre in the Torre Valley. Spent about a month climbing there in January a couple years ago. And next we have a picture from Chamonix. That's doing an alpine climb with Mount Blanc in the background. Finally, picture my girlfriend Lana and I last summer with that's the Chief in Squamish, Canada, in the back. So yeah, I've just really enjoy rock climbing. It's taken me a lot of awesome places, and I know everyone on this call, we all have our jobs, but our hobbies outside of work, I find climbing's really fulfilling, and that's what I enjoy to do.
Thanks, Ryan. Well, Ryan's a hard act to follow. He's kind of working on Most Interesting Man Alive, so I'm a little more boring. I'm a girl dad. I'm in my dad era. Most of my time is spent doing kid events and sports and whatnot. But when we do get some free time to actually have a vacation, we generally go to where my in-laws live down in El Salvador and get to enjoy some fishing and activities down there. We don't get to do as often in Tennessee. So nice to meet y'all. So we're here to talk about the MABR. I thought on the beginning of this webinar, it would be best to try to explain it as a product, and then we would work our way into a solution. So the MABR that Fluence provides, we utilize a flat sheet membrane. If you see this picture on the right here, where you have the flat sheet laid out, you got a little over 850 feet of membrane laid out on the ground. And what we do is we take a membrane, we cover it with the air spacer, and we put another membrane on top. And what we do with that is we weld it together around the perimeter of the sheet to create a void for the air to pass through. The air will eventually diffuse into the wastewater, and we'll get to that in a little bit. But then once we weld those pieces together, we create that air pocket. We would have a water spacer on the bottom, and we roll up the membrane to work into these towers that you see here, and they can be stacked. Generally, we go 2, 3, and 4 high. The amount of towers is really driven by the depth of the wastewater to submerge them in. And then there's a coarse bubble array that goes underneath, really acting as a way to displace the treated wastewater with raw or less treated wastewater within a basin to promote mixing and treatment. So there's going to be a little bit of a recurring theme on my side. I apologize, but I want to make sure if I get anything right out of this that I drive home that you hear the word membrane. Initially, most folks, you know, they know what membranes do, and those are used as filters. They're used as ways to physically create a barrier to promote uh, inlet water of some quality to an effluent water of almost pure quality. In this process, we're not doing that. I mentioned before, we're putting air inside that sleeve that we've created with that air spacer, and we're using the membrane as a surface to promote biofilm growth. The biofilm that we're growing, it's a nitrifying biofilm. It only grows to roughly 200 microns at max, and it doesn't have the stability to continue growing. So we end up with a condition of a membrane application of being a terrible condition where we've wanted to, where it's covered in biofouling, and that's exactly what we want, versus the traditional method of a membrane needing to be clean. So with that growth that we're promoting, it's like I mentioned, it's a controlled condition for the thickness, and a main point on operational operationally speaking for the membrane is that there's not an intent to need to clean it. There's not a maintenance mechanism to this. The intent is for it to be deployed, and dissimilar to the physical barriers of membranes, where you have to be exchanged out every so often just as part of a life cycle cost. The intent of these is to have a 20-year life cycle, a 20-year deployment, and just the mechanism of the durable materials we're using, as well as the way we're using them. So we're talking about membranes here. I have a aeration genesis, if you will, of the history here, but you know, it's strange to kind of have a membrane on this chart. And why is this here? Well, the MABR itself, although it's a membrane aerated biofilm reactor, is the acronym. The membrane is just a means of diffusion in the wastewater. So if you kind of, from a power consumption standpoint, to understand the efficiency, you can kind of see as the different versions of aeration went on through the years, you can see that we're making progress to getting to a more efficient mechanism from where we started of introducing the air into a basin. The MABR tower itself is a pretty large leap in the technology of just getting air into the wastewater. And from a perspective of power consumption, if the kilowatt hours don't generally equate to you understanding how much less energy it's going to take, we've broken down on a 150,000 gallon a day application. Where in the beginning you'd be somewhere around $170 a day, and working your way down through the technologies. I would say fine bubble would be the most common now, currently being utilized, and making that jump from almost $100 a day to just $13 a day, at 15 cents a kilowatt. All that said, really trying to drive home. I'm an analogy guy. I stole this analogy from somebody, that if you're looking at conventional aeration versus using an MABR, it's like going from a carbureted engine that where the conventional aeration is just flooding the whole basin with air and hoping for even mixing, to, you know, move into a fuel injected engine where the MABR targets the oxygen precisely where the microbes need it, and just drive that efficiency, lowering the horsepower per pound of BOD removed. So we went over the components of how we put this together. Part of what we should also go over is how the air flows through this. So as I mentioned, we have the membranes, we have an air spacer, we have the water spacers. They're wound up into what we call a sushi roll here. And we're introducing air on one side of that sleeve and we're letting it exit on the other side. It's a very low pressure scenario. We're less than 1 psi within those membranes. Kind of a key to the low pressure is being that airspace that goes in between, because we've now physically made a void with that airspacer where no matter how deep, excuse me, we're submerging these towers, we don't need to overcome the hydraulics of the mixed liquor we're putting them into. I did mention that there is that intermittent scouring that goes on to displace all the fluid that's been treated with fresh, raw water, kind of making the analogy to an airlift, and just replacing with water that needs to be treated. So we are growing our nitrifiers just directly on that membrane face, and we get into a differentiator between like an RBC technology where you're growing a heterotrophic biofilm where it's going to require frequent cleaning and it gets lots of buildup, to a stable environment that's intended to not be maintained as long as you're following the treatment targets. But and this vertical lift that happens through the membrane during operations also helps limit or create an environment where a scum layer cannot exist. You're not getting the membrane, you're not losing surface area of the membrane due to a scum layer or just getting airbound with vapors that come out of the process, where it's allowed to, it's able to freely flow through up vertically. Just a quick little visual. So if you look at this line here, that would be the membrane face, and if you can imagine, there's another one on the other side, so you can see the oxygen flowing between those two sheets of membrane. We're growing a biofilm here on the face that's specifically for nitrifying ammonia. That ammonia is now going to be converted into nitrate in our suspended mass, which is where our heterotrophic growth is. And from the nitrate, we're converting the BOD as a carbon source to make the nitrogen off gas. So again, on the membrane face itself, we're taking care of all the nitrification, and once we get into the suspended mass surrounding that vessel, we're getting into the denitrification component of this. So we're able to achieve both within the same basin. So it's an interesting technology because there's a simplicity factor to how this works and how we apply it to the MABR plus the low DO process. But what it does allow us to do is be pretty flexible on the way we apply it, whether we're applying it to a package plant, to a large conventional plant, as a side stream treatment. It's got the MABR itself is the primary mechanism is that nitrification piece, and the supplemental processes we do behind it is where we get our denitrification. But it allows us to stick it in a bunch of different types of variations of applications. Laying out just a general overview of the process. Depending on how much phosphorus you're needing to remove, is kind of how we select this anaerobic basis. Not dissimilar to a lot of other technologies where it's a time mechanism, but what does differentiate it from other options is we've removed all the internal recirculation streams aside from the RAS, so there's no internal nitrate recirculations, which does allow for the protection of this anaerobic zone from getting some commingled nitrates and introduce them to the EBPR process. But from that point, it's anaerobic. This MABR zone's an anoxic, and then you have your aerobic zone. That zone, particular to the Fluence process, we're running it at a low DO to promote that denitrification and the remaining nitrification needed. And the point where we decide to stop adding MABR towers and going to fine bubble diffusion in the zone is really just an economic choice where the MABR's cost is outweighed by the efficiency of the fine bubbles following it. And from an operator standpoint, while it's in the field, when it's deployed, this is very similar to a normal condition to a conventional wastewater plant. The way it's flowing through, there's not a lot of levers for someone to have to operate and need to configure, and you're not in the position where you have 10 different variables where you need to make your adjustments. We're really looking at 2 control points for this type of treatment, where in the MABR area or the anoxic zone, you're keeping track of your nitrate production, and that's how you monitor the nitrification going on in that basin. And on the back end, you're just looking at your DO. Once you get in with those control points with your flows, it's a very simple process, not a lot of moving parts. What also is interesting about this, since it is a simplified process, is we're able to containerize a lot of these technologies and use them as building blocks to go after applications in a different way, where a small application can get at or a little below 2,000 gallons a day out of a 20-foot container. You have an entire treatment plant that fits within that small container, and you work your way up into the different sizes for different flows here. But we've taken the modular approach where we can break out different variations of application, where we kind of be a little more agnostic to what does go in, whether it's a clarification process on the back end, putting an MBR on the back end, and the amount of towers we need to work within these basins. This large MABR can have anywhere from 1 to 5 towers within it, and the medium size can have 1 to 2 in it. It does allow us to be extremely flexible per the application. So another interesting note for MABR, when you look at it compared to different treatment methods, we've picked out a couple here. I don't know if you can see them well or not, but activated sludge down here at the bottom of the graph. We have MBBRs, we have BAFs, and we have the MABR. We looked at a lot of different treatment solutions. Cold weather does become a part of the conversation, even for us as well. But what you will notice is with some of these other treatment methods, you start, as your temperature rises, you start to get into more of a hockey stick of your nitrification process, where the MABR stays relatively stable on its transition up in temperature. And really that a mechanism of that is that the biofilm's self-regulating itself in the cold conditions, and that the way I explained the water being displaced to the air and rising vertically, it's creating a counter diffusion that decouples the oxygen part of the calculation from the temperature when we're nitrifying. And it's just creating a more favorable, stable environment for operations. And as your condition change and a quick warm up or a quick cool off on the water seasonally, you're not having to make large adjustments constantly to chase the temperature up or down. It's more of a slow, controlled movement through it. And on the product side, just the things I hope I was able to drive through is listed up here. But the big things to note for me is that when looking at an MABR, the membrane mechanism is it's a diffuser, not a means of filtering. And the nitrifying biofilm is a stable, controlled growth that doesn't require cleaning or operational challenges, and that the stability of the treatment method in varying temperatures. I'll hand some of this off to Ryan now.
Thanks, Dustin. So we wanted to present a case study today. We're going to talk about Dow City, which is a small town in western Iowa. Um, for those not familiar, I small point on a map. The town's just under 500 people population, but they had some treatment challenges with new updated flows that we'll review. So next slide, Dustin. The problem that we have in Iowa specifically, Iowa has the most wastewater lagoons out of any of the states in the U.S. Of more than 700 lagoons in Iowa, 500 of those are controlled discharge lagoons. So those would discharge twice a year, typically in the spring and the fall. 200 of those are continuous discharge, where they're discharging year round. The challenge that Iowa's facing in particular is that most of these lagoons were designed for BOD, TSS, and pH, specifically, removing those constituents, BOD and TSS, and regulating your pH. The DNR a few years back mandated, these new requirements that included ammonia and E. coli. And the problem was that, most of those solutions out there are very capital intensive. And this city, Dow City, we were just talking about, small town, small population. A lot of these rural towns just simply can't afford these large capital intensive solutions that are out there. So next slide, let's just go over the basics of a lagoon. For those unfamiliar, your typical lagoon is just basically excavated hole in the ground. It's older technology for wastewater treatment, and you're relying on basically wind or air in addition to the photosynthesis from the algae that's producing oxygen to introduce oxygen into the wastewater. So you have that wind moving across the water, as well as the algae that's basically taking that sunlight, converting carbon dioxide into oxygen. That's how a lagoon introduces oxygen into that system. You then have aerobic bacteria that is working to remove the BOD from the system. And, typically these lagoons have long retention time. So Dow City, there's 2 cells in that lagoon. Each are sized for about a half a year's worth of retention time. So basically you're requiring long retention times in order to remove that BOD. The challenge is that with these new updated ammonia requirements, what we're seeing is that a lot of these lagoons are failing, specifically in the wintertime, failing the ammonia removals that are now required by the DNR. So next slide. I saw that Nathan was on the call. So Nathan Seberg, he's in the bottom right corner. Him and Craig Just basically brought us this project a few years back. We met Dr. Craig Just at a WEF Craig was basically given a grant from the state of Iowa to pursue alternative options and to really look into new innovative technologies that could be a solution for small towns like Dow City. With the help of Nathan, who actually provided a lot of these photos, he helped with the installation. We've basically been piloting this technology in Dow City for ultimately the DNR's approval, which we actually just heard recently that the facility plan was accepted in Dow City, and we're excited to be one step closer to gaining our full approval of this technology in Iowa. Next slide. So again, I was saying, the cost issue was a problem. We had ISG, who's a large consulting engineer in the Midwest, take a look at this project. And when they were looking at costs for Dow City, they analyzed our solution against 2 other solutions, a submerged attached growth reactor, as well as a covered aerated lagoon. And as you can see from that table, we came in significantly cheaper from a capital perspective on installed cost, on what that would look like to basically provide this town a solution. When you're looking at these small towns that are likely going to have to take out loans for a new treatment plan that's eventually going to be passed on to the ratepayer, you know, these small rural towns are excited about basically utilizing a system that's less than half the cost of whatever else is out there. All right, next slide. So the system that we have installed at Dow City is an Aspiral M2 Plus. Just a quick name or a quick note on the nomenclature there. M stands for medium, so we have our S, M, and L series, small, medium, and large. The M series, we max out at around 30,000 gallons a day hydraulically. The 2 denotes that there's 2 MABR towers in that container. And the plus just means that we have a media filter on the back end. So for stricter effluent requirements, typically when we're targeting 1010 BOD TSS, that's when we can include a media filter to achieve those effluent requirements. Next slide. So real quick, we're gonna just look through some pictures of the pilot that we have installed there, starting with the installation. Next slide. So the idea of showing you all these pictures is just to showcase how efficiently and relatively easily we're able to install one of these systems. You can see the 2-cell lagoon there in the left photo. You see some excavators pushing dirt. That's at the end of March 2024. So just keep in mind that's sort of when we're beginning this install at the end of March. Early April, pouring that pad of concrete that the container will ultimately sit on. Next slide. We performed the lift early May, so just over a month after they started pushing dirt. It's a 40-foot high cube container. We do custom design and fabricate these to be watertight containers. These aren't repurposed, freight containers that you might be used to. But for a contractor, these 40-foot containers are easy to understand. Any contractor will understand how to perform a lift or how to move these containers around. Makes it really easy to do an install like this. Next slide. It took a day and a half for them to construct a building. So because of the really cold weather experienced in Iowa, or for any application, rather, it's important to think about protection for your operators and just protection of the equipment. So the decision was made to basically house the container inside a building. This building went up in a day and a half. So really low cost building, but provides great shelter and great protection around the unit. And you can see there, that was the end of May. And now here we're at the beginning of June. They've plumbed up the interconnecting piping. You can see the dock just off of the building. That's where the feed pump is located. And we're treating water early June. So that was basically end of March to early June. It's about a 2-month install for this whole process here. Next slide. Okay, so now we're going to talk about some data that we've received and just show how we're able to effectively remove ammonia during the cold winters that Iowa experiences. So we started out with the startup, just leak and aeration tests, filling the containers with water, checking for leaks. That's just part of our startup. Next slide. We typically like to seed our systems with sludge. So that looks like basically organizing a vac truck, working with some local municipal wastewater treatment plant, getting some of their activated sludge and introducing it into our system and recycling it. that basically introduces biology to our system. That biology will then basically latch on to our membrane and start to grow. That's where we start building our biofilm. Next slide. So you are what you eat. The idea with this is to just show how we really have operated the Dow City pilot in two completely different biological ways. So this first way that we're going to talk about is a biofilm-only process. The dock that you see there is located sort of at the perimeter of that lagoon, and these lagoons each receive fresh wastewater from an inlet pipe that deposits the water about in the center of each of those lagoons. So if you can imagine, these are each have about a half a year's worth of retention time. You're depositing that fresh wastewater in the middle of these lagoons. We're feeding our system from the perimeter of the lagoon. So there's a lot of time for that algae in the lagoon to basically act on the wastewater. And what we found initially treating the wastewater was that we had really diluted influent, really low loadings as far as ammonia and BOD were concerned. And basically what that resulted in is us operating in a biofilm-only process. Next slide. So you can see here, we just seeded the sludge. Our SSV was quite high, right around 700. But over time, because of the low nutrients that we were feeding the system, we actually lost our sludge. We lost our MLSS in the system. And, 2 months after the fact in August, we essentially have almost a clear, zero SSV. We're basically just passing this semi already treated wastewater from the lagoon, from the algae into our system. Next slide. Despite that, we're still able to show that we can effectively remove ammonia even at these colder temperatures. So the x-axis here on this graph is dates. We're looking at December 24 through June 25. And what you'll see is that, February, March, these are the coldest times of the year when this lagoon is actually under a sheet of ice. We have regularly really cold wastewater temperatures during this time. Ammonia, which again is not specifically targeted by that algae or by the lagoon, we're still introducing ammonia into our system at lower concentrations, but we're still seeing upwards of 10, 15 milligrams per liter of ammonia. And we're able to effectively remove that ammonia down to the levels that are required by the DNR. Next slide. So here we're showing, Nate was great about taking temperatures and all this data for us. And what we can see is that at temperatures as cold as 36, 37 degrees Fahrenheit, temperatures that you typically would not expect to be able to nitrify and remove ammonia. We were able to show that we could continue to remove ammonia at pretty decent rates there. So 60, 70% ammonia removals. So after obtaining all this data, and I had the great idea of installing a baffle to essentially change the feed source. So earlier, if you remember, we had that dock right off of the container. We essentially, the idea was, hey, let's try to, obtain some data and show the DNR that we could basically treat full strength waste. Since it was still a pilot, we could not pull directly from the influent lift station. So the next best thing that we could do was try to intercept that wastewater while it was still full strength before it had the opportunity to basically interact with the algae and the rest of the lagoon. So that baffle that you see, next slide. That baffle in the middle is actually a floating dock with rubber sheets sort of all around and a chain that basically holds it down. And the idea was to position this over that influent pipe that feeds the lagoon system. So from earlier when we were working with that biofilm-only process, now we have these feed pumps that are essentially intercepting the wastewater while it's still full strength before it's been treated by any biology, and we're directing it straight into our system. Next slide. You can see here just the black color inside that baffle. We found that this portion within the baffle quickly became anoxic or anaerobic. We're just basically, yeah, we have raw wastewater, so that's what you would expect. Next slide. And basically after that baffle was introduced and we started pumping from the baffle, you can see over the course of a month, we're now starting to build sludge back up into our system. We're going from a biofilm-only process to an activated sludge process. So you can see the SSV starting out mid-July, we're at about 150, and middle of August, we're back up to around 700, 750. Next slide. So after the baffle, this graph here, again, the x-axis is dates. Right about in the middle is June when Nate introduced that baffle, and you can see just how those concentrations of ammonia have changed since the introduction of that baffle. So before we're dealing with, maximum 10, 15 milligrams per liter of ammonia. Now, with the baffle, we're actually seeing ammonia concentrations consistent with what you'd expect in typical raw municipal wastewater. And what you can see as well is that our ammonia concentrations in the effluent actually improve in the sense that we're removing ammonia even better as an activated sludge system, which is how the MABRs were really originally designed. We designed the spiral systems to work as an activated sludge system. This was sort of a pilot for us, just to learn, well, how will it look if we run it as a biofilm-only process as well? So what we're showing on this slide is just how we're able to accommodate both those different conditions and still reliably remove ammonia from the system. Next slide. So again, here just with some percentages, June through November. So November starting to get to those much colder months. You can just see that we're consistently achieving pretty great removal rates for that ammonia. Next slide. At that point in November, so the two dotted lines that you can see here, that first dotted line on the left, that signifies when the baffle was installed. The second line in November, Nate suspected that the baffle wasn't quite positioned correctly, or might have been slightly off center from that actual influent pipe. So he went and he moved that, and what you can see is we're actually from November 25 on receiving even higher levels of ammonia, all the way up to 60 milligrams per liter. So just three really different sets of data for different ammonia concentrations and conditions, but with all three of them reliably removing ammonia. Finally, just wanted to present some data that we got back from the lab. You can see here that in addition to BOD and nitrogen, which is what our technology is, that's why we're pursuing this market in Iowa. I'm really excited about working with these lagoons to remove BOD and nitrogen. We also are seeing that we're really removing pretty high rates of phosphorus as well. That's through this EBPR process, where essentially the bugs in our system are absorbing the biological phosphorus, and ultimately that ends up in your sludge and being removed from the system when you remove your WAS. But yeah, we're basically have data here to show that we're able to consistently remove BOD, nitrogen, and phosphorus in a variety of different conditions. All right, back to you, Dustin.
Okay, thanks, Ryan. Well, from a power consumption perspective for the application Ryan was just reviewing, what we really drove down to on this was we're roughly about $5 a day average for this 30,000 gallon a day plant. So to make an analogy for the power consumption, you're looking at similar to a single family home to run this plant. Really, the uptick in power usage has been attributed to just turning on the heater in that building to get that room above freezing. It's not a room that's kept up to a normal temperature like inside the house, but we do need to stay above freezing. And we've made an analogy to a higher utility rate since Iowa does have lower energy rates, but it's still under $10 a day. So from the perspective of temperature, we've got a write-up that Black & Veatch has verified some of our treatment approaches at one of our larger conventional plants in Israel. But one of the key things that came out of this review that they've tableized here is the reduction in volumes for reactors and clarifiers. So some of the magic of the MABR is the reduction in volumes required to perform the treatment, where at a 15 degrees Celsius instead of at a 7-day SRT, we're drifting to 5. And when we get to a higher temperature, kind of on that chart that I showed earlier, as you go up in temperature, the technologies become near peer for nitrification processes. It does transfer over to the bioreactors and clarifiers as well. What doesn't go away is the energy savings. So similar to conventional wastewater treatment, there is a stability between seasons of cold to warm, where you're using similar amounts of energy to perform that treatment. But what you do see is the stability and the reduction of energy using that MABR, coupled with that low DO process, where we get the full energy savings, where we're reducing the bulk aeration, replacing some of that bulk aeration with the process air that I talked about before, that being the air that we're pumping through the membrane that we already discussed. But you also can see a very significant removal and pumping, and that's part of the internal recirculation loops that we're able to remove from the treatment process entirely. And from that point, that is the end of my end. Brian, you have any summary comments you want to go through?
Yeah, if you throw on the next slide, just kind of wanted to show. Do we have? Yeah, just sort of a kind of overview of this equipment and advantages that we're seeing, specifically around Dow City, but just in general. We talked about the speed of installation there. This was a 30,000 gallon per day plant that we went from moving dirt to treating wastewater in a matter of 2 months. We talked about the cost competitiveness of the system, how we had ISG, prominent consulting engineer, look at a few different technologies, and basically we came in less than 50% of the installed cost of what our competitors were doing. From a pre-engineered design, our spirals are it allows us to understand our costs and basically provide these systems at a lower cost to our customers. The total nitrogen removal, we talked specifically about ammonia removal in this webinar, but the technology itself is great at those projects that do have a low total nitrogen. That's when you also are required to remove nitrite from your wastewater. We talked about the few different feed sources, basically functioning as a biofilm-only process, as an activated sludge process. We're able to accommodate different flows. We've also done some projects where we're treating side streams to a system, to those larger systems. Our nitro process basically allows us to specifically target those high strength side streams common in larger municipal facilities. And as Dustin shared, the operating costs for that plant for Dow City, we're working off of $5 a day for an operational cost. I know we've done some work with developers and private utilities, and oftentimes that's a really important factor for those sorts of customers. Is the capital CapEx is one thing, but what's this plant going to cost to operate for every day for the next 20 years? That's a really important consideration. And as Dustin was sharing, the MABR is a standalone technology, doesn't require cleaning. We do have coarse bubble diffusers that we install below those towers that intermittently mix and basically slough off any excess growth. But other than that, we don't require or see the need for the membranes to ever be changed out or to be serviced. So it's just a benefit from an operational standpoint.
I think from that point, we're good for questions here, Jessica.
Yeah.
Yeah, great. If anyone has any questions, feel free to just throw them in the chat and we'll answer them as they come in. You can add them in the Q&A section or the chat. Either way, I'll look through both.
Mark, to your question about the E. coli, so the facility plan for this, the Dow City installation was a pilot. We're intending to install an actual full-scale plant, but we were actually just sending our treated effluent back to the lagoon for a standard, for a standard installation. That would look like us including chlorine disinfection or UV disinfection, whatever the customer would like. We're currently not disinfecting at Dow City specifically because we're not yet discharging into the local stream.
I think there was a follow-up question there from Mark as well on the sludge. Ryan?
From the sludge, I'm not sure I'm
You see
seeing
that?
that.
He's saying, what were sludge levels in the lagoon and did this process positively or negatively impact the sludge?
Yeah, Nate, I know he takes a little boat out to service the dock, and I think conversations with him, there's about a foot or so of sludge on the bottom of those lagoons. A typical lagoon process, you're just accumulating sludge over time. I don't believe there's a super reliable way to remove the sludge from the system. But I'm not sure that we really understood or studied or looked at the impact specifically on the sludge inside the lagoon.
Lele, the mining application question. I think I'll get your information, and I'm not aware of us doing a mining application. I know we've done a lot of work in oil and gas and things like that, but I'm gonna have to probably research your question a little bit and get back to you. Sorry about that.
Yeah, and Annabelle, again, the excess sludge from the MABR, it's currently just being deposited into the lagoons. When this does move to a full-scale installation, that'll be in some type of sludge holding tank that would, periodically be vacked out and brought to some larger municipal facility for those larger facilities typically will have anaerobic digestion and actually dewatering. For these smaller plants, it's typically not economically feasible to include dewatering equipment. It's just too expensive. Mark, the algae in the lagoon. So the only real negative that we saw from the algae was actually within the media filter. So the media filter that we include on the back end, we were finding that it was just basically clogging with the algae. We were basically taking in so much algae to our system and running it through the media filter that it was just backwashing so frequently that the operator actually decided to not utilize the media filter. We did find that once the baffle was constructed, we're basically able to intercept that wastewater before algae was introduced to the system. So at that point, we're able to essentially use the media filter again. So to your question, Lale, about the temperatures and the minimum temperatures. So our standard, process calculations or designs will typically design for a low temperature of 8C. We recognize that. We just presented data of ammonia removal at 2.5 degrees Celsius. But I'm not sure that we have data specifically around 1C. We do tend to design around a low temperature of 8 degrees Celsius. And as far as if it's size based, absolutely. So we'll consider the flow rate of a system. We'll consider the design temperature. We'll consider the loadings. All that goes into our process calcs to determine, what a spiral best suits that project or that wastewater. And for those larger projects, yeah, we're looking at those Subre installations where we're installing those towers in a concrete basin.
I think we got everybody. I'm trying to scroll through the questions here. Jessica, if you...
I'm not seeing anything else, but good. That was a good question round, actually. So, yeah, that looks like that's it. And Sherry put in there if anybody needs a training certificate or participation to send her an email. Otherwise, it looks like that might be it for you guys.
And Lele, with your question here about being placed outside or in a building, I would say if we're going down the path of 1C for your water temperature, we're gonna lean pretty hard into it being in a building of some sort. At a higher outdoor temperature, we can look at different ways to insulate, where we've done in like New Mexico, where we've insulated the outside of the container, where we put some siding on with the working hand in hand with the contractor to fit that on. But if the water's getting to 1C, I gotta imagine the outdoor temperatures are fairly extreme. All right.
Great.
Well, thanks everybody. Oh, you have another question? Say hand up.
Nope. I think we're good.
All right.
Awesome.
Well, thank you everybody. And Lele, I'll reach out to you about your mining question. Let me just call the process team and ask some questions real quick, and I'll get back to you. Thanks
Great.
all.
Thanks, everyone.
Thanks, everyone.